One.
Okay, so today I'm going to be talking about playlist 13, which is a closer look at exponential growth rate. So with our exponential equation or differential equation, we have dp over dt is equal to kp, which means the rate of change is proportional to the population. And if you solve that, the general solution is p is equal to p sub 0 e to the kt. Then time just goes over sort of an example. It's like, okay, looking at half-life, when is the population twice its normal value? When will this occur? So looking at the general solution, the e to the kt when that is 2 is when you can find the half-life. So he basically derives the half-life slash doubling time. He also refers to it, doubling time equation, which is natural log of 2 over k is equal to t. And then the rest of playlist 13 is a look at the logistical model. So first she sort of compares and contrasts the exponential and logistic model. With the exponential model, you have sort of there's no limit. It keeps on growing and growing, which isn't really helpful or applicable to like real life things such as like viruses, which eventually like level off at some point or don't just like grow in proportion. So with a logistic um, expression, the differential equation is dp over dt is equal to k times the percent of the remaining capacity times p. And what this means is the rate of change is equal to the population times the percent of the remaining capacity. So there is L, which is like a limiting factor or a carrying capacity, if you want to talk about biology. And to um, further, I guess, add more stuff into the equation to make it more specific, um, that equation will become dp over dt is equal to k times 1 minus p over l times p. And the reason why you have 1 minus p over l for the percent of the remaining capacity is for, I'm going to use his example. If you're at 30 and the max is 100, then you're 30 over 100. So you're like, that's 30%, using 30%, which means you have 70% remaining, which is zero point 0.7 as a decimal. So that's 1 minus wherever you're at. And then if you wanted to solve that, which we're not going to do, that all basically boils down to, at least the general solution is p is equal to 11, not 11, sorry, L over 1 plus a, which is a constant, e to the negative kt. A is also described as L minus p sub 0 over p sub 0, but isn't quite relevant now, but that's another way that you can define A. And then the last video is 11.7.2, finding the peak, which is basically finding what is the max rate of increase. And another way to word that would be, when is the second derivative 0? So from your differential equation, dp over dt equals k of times 1 minus p over l times p. If you take the derivative of that, so you have k minus 2kp over l and set it to 0, and solve for p, you will get p equals L over 2, which is the inflection point and will always occur at half of the limiting factor. So whatever that L value is. And that's basically it for playlist 15. Does anyone have any questions?
I just wanted to point out one thing.
Yes,
So I'm going to share my screen here.
yes.
So when we're talking about exponential growth rate, so that we're talking about either when something doubles or halves its quantity.
Mm-hmm.
So basically, the smaller the t is, the lesser time it takes to double, and then also the other way around too. The smaller the t is, um, the lesser time it takes to halve. So it just means that the curve is going to be more steep. So and then this is something that we kind of find out from our example problem last time, which is which is a fundamental property of exponential functions. So the amount of time it takes for the quantity to double or half one time is going to be the exact same amount of time for it to double consecutive subsequent times.
Yes, that is
So I
correct.
just wanted
Thank
to
you. I
point.
left that out.
Yeah.
Does anyone have like any other comments or questions?
And we're good.
Alrighty. I think we're good. Yeah.